Okay, so now we will continue with the second part of this lecture, and now we will go into antenna measurements. So this is really what you will do next week when you have the lab of measuring your patch antenna. So in the lab you had this week, you were measuring the S parameters and you were tuning your antenna to resonance. You were tuning it to 50 ohm and so on. And now what we will do next week is to determine the radiation pattern of the antenna. So there it of course comes in, how do we measure the things that you need to measure when you're going to determine the radiation patterns? And that's what we're going to talk about today. So we will start here with some typical antenna measurements. And the antenna measurements can be done for different setups. A typical one is a far field setup. There is a near field setup. So one thing we can see here is that we need to start to distinguish between far field and near field. I have mentioned that before in the course, but we have not really digged into it. Now we will dig in a little bit more with what does it mean to be far away, for example, from this patch antenna? How far away do you have to be far away, which means the far field? Then we will look at a few different ranges here. So we have a compact range, near field ranges, and so on. Specific absorption rate comes into measuring the absorbed power in the head from a cell phone, for example. Okay, so a typical measurement of an antenna or antenna system is the antenna you can see in the picture. You can see it here too, same antenna. And to measure these ones, you of course need two antennas. So we have this antenna here. We call it antenna under test, sometimes AUT, that's it here. So that is the antenna we would like to determine the properties of, which means, for example, the gain of this antenna, the directivity of this antenna. This is what we would like to measure. To do this, we need another antenna, which is some source antenna here, or measurement antenna. So that is an antenna that we use in the measurement. So in a typical case, this is a transmitting antenna. So this one is sending out waves, and then we receive a signal in these ones. So in most cases, your antenna is passive, in the meaning that it receives a signal transmitting from the source antenna. And then what we can do is that we can then rotate this antenna under test. So for example, you can rotating it around here, the Z-axis. Then you can get, in some ways, a cut of the radiation pattern for a fixed theta. And then you could think about, you could take the source antenna and, for example, move that in the angle theta. So first you measure, or you illuminate it from up here, and then you move it down here, and then you move it there, and then you move it down there. And then you, all the time, you rotate your antenna under test one turn, so 360 degrees. And by changing theta from 0 down to, for example, below here, 180 degrees, you will get the complete 3D pattern of your antenna. So that means that if you go from one theta to the next theta, you need to rotate one to 360 degrees, move to the next theta, rotate, and so on. And this, of course, takes a lot of time. So in many cases, you only do some of these rotations, and then you get cuts of your radiation patterns instead. So we will look at a few different cases there. In this setup, you would also measure in some ways the far field measurements. So that means that the distance here you have some distance between them, that needs to be sufficiently large to be in the far field. And yes, as I mentioned here, the transmitting one is usually the source, and also in many cases you only take cuts of these ones. And now if you think you do these measurements, then of course if you would have a building here, you might have a wall here, then the signal might bounce in this wall. So if you're doing this in an indoor environment or outdoor environment where you have grounds, the propagation from the source antenna to the receiver doesn't have to take this direction. It could take like this direction, it could hit something and that can be radiated up here. And if you do that, you don't measure the correct thing, because you need to know from where the signal is coming if you're going to determine the radiation pattern. So that means that we need to remove all of these environmental reflections. We need to take them away. So the wave only propagates directly line of sight from the source to the receiver. It shouldn't go any other direction, no multipath propagation. Those we want to take away. And that is done by putting these measurements into what's called an anechoic chamber, which is a radio quiet room which has no reflections. And that you're going to measure your antenna in next week. Next week, you're also going to go into an acoustic anechoic chamber, which is one of the most quiet room you could imagine. It's a room where you have no reflections. So when you speak, the wall doesn't reflect your sound back. And there you will, in some ways, sense yourself how it is to be the antenna in the antenna chamber. So what it means to be in this quiet room. Because you can listen, but you cannot really sense the microwaves, but you can hear the acoustic waves, and they actually behave fairly similar there. So you can use that as an understanding of what's happening in these anechoic chambers. Okay, so then we can ask, how do we do the measurements? So what have we learned in this course? I mean, one of the first things we learned was this freeze transmission formula. And that said, if I receive a certain amount of power, so I measure now in my antenna under test, there I can measure the received power. I have my test antenna, there I can transmit a certain amount of power. If I have my other transmitting antenna, it's a known antenna, I know the gain of that antenna. I know the wavelengths I'm using because I know the frequency, I know the wavelengths, and I basically know the distance between them, and I know what 4 pi is. That means that from this I can determine in these cases here the gain of this antenna. So here I can now get gain R in this case. So that is one way of actually doing these kind of measurements, but it doesn't work very well. And the reason for that is that even if freeze transmission formula is very good, it's very accurate and so on, it includes things that we usually don't really have control about in these cases. Like I mentioned here, yeah, I know the received power, I know the transmitted power. In reality, you have your antenna, for example, this you have as an illuminating antenna, it's a horn antenna. To this one, it comes a cable, and there are quite a lot of losses in these cables. And maybe you don't know those losses, which means that you cannot really use freeze transmission formula in that case because you don't know the transmitted power. The next thing in this is actually that the distance here is in many cases non-trivial. So if I take these two and I put them up here, my horn and my patch antenna, from which point of this horn should I measure the distance? If I move it very far away, like 50 meters away, it doesn't matter if I measure from inside here or from the edge here. But if they are like 2 meters away, it's quite a big difference to take different points of these ones. So it's actually not trivial to even know what the distance is between these antennas. So that means that we actually don't measure using the freeze transmission formula. That is not accurate enough to determine the gain, for example, now of your antenna. You cannot really use it in a good way here. So what's done instead is that we do 2 measurements. So first you measure with a known antenna. So let's say I would like to determine, for example, this antenna here. I have my patch antenna. I don't find my patch antenna. Ah, here. So let's say I would like to measure this patch antenna, like the one that you have built. What I first can do is that I then measure from transmitting with this one, sitting at a fixed place. I measure like this antenna. And then I do another measurement with a known antenna, for example, these dipole antennas. And then I just take the quotient between everything that sits there. This is the same antenna. So in both cases here, the transmitted power, the gain of the transmitters are the same. The distance that comes in is the distance for the transmitter to the receiver. Of course, it can be a little bit discussed. Is it to this point of this receiver or this one? But at least I don't have to deal with the distance to this transmitter. So that one disappears. And the lambda here disappears. And the only thing I get out here is that the gain of my antenna compared to the gain of the reference antenna, typically this one, is the quotient between those two powers. And this is the way that you will measure it. And this is the typical way of measuring these type of antennas. So you actually always relate your measurement to another antenna, and that antenna is assumed to be known. So that is your reference. So you compare it with a different antenna. And that you can do by just taking the quotient between the powers that you receive. So we measure this gain relative to antenna 2. And if you do this in dB, in most cases this is written in dB, it means this is the 10 logarithm and then the quotient between the two gains. And you write that in many cases here then as dB2, where dB2 stands for dB relative to antenna 2. So if I did it here with respect to this dipole antenna, I would say that my patch antenna has 3 dB dipole. I would actually do it in a reference to a dipole. So the common reference here is that we have an antenna. So we have a reference antenna. This is the typical reference antenna done in measurement. It's a sleeve dipole. I've shown you the same picture before. You can really see the top of these ones. That is where the dipole sets, and the rest is just a cable that goes down. There are something sitting on this dipole, and that is things that removes the current from your dipole. So the radiation actually comes very accurately from this dipole. And that is then calibrated somewhere. Typically, it went to another measurement chamber that measured this antenna and determined that this has this gain, for example. And then you know that somebody else have told you what it is. And then you measure relative to that antenna. And a half wave dipole here is approximately 2.15 dB or dBi. And if you measure relative to that one, you will say that your patch antenna might be 3 dB dipole, or dBd in this case. So it means that it measured relative to a dipole antenna in that case. If we use a monopole that you will do in the laboratory session, you will measure in a unit that's called dB monopole. So that is the unit that you get out. And then if you know what the reference is, then you can calculate your own gain for your own antenna. Otherwise, you only have it in this dipole setting. And now the pictures there disappeared on the previous one. This is called a cantanna. We used to actually measure relative this one. I will talk about that antenna next week. That is the simplest antenna that you could ever build if you would need to. It's sufficient to go to, for example, Ikatuna and buy a can and doing some holes and of course put everything at the right place. And you can measure relative to this antenna too. We used to do it in this course. And that means that we have a normalization to something. And in many cases, when you look at the gain of an antenna, they actually give a unit of it that's called dBi. And dBi is the regular dB. So in many cases nowadays, it's not written out. Most cases, I don't write dBi, I only write dB because it is the same thing. If we don't write anything, we assume that that is that normalization. And the normalization is here with an ideal isotropic radiator, which is the regular dB because that is how we measure gain. That is relative to an ideal isotropic radiator. So sometimes it says dBi, sometimes it just says dB of these units for gain in these cases. And of course, to do this, it's also important to consider matching and polarization. So for example, if you measure your patch, you have a dipole, you have to make sure, of course, your dipole is first aligned with the transmitter and so on. And you have to align your own antenna also with these ones. And they have to be matched to get accurate results. So that is units that you can get out. And when you then do the measurements, we will not measure the full 3D patterns of your antennas. So you will get 2 cuts. So when you attach your antenna to this turntable, so this is basically what it looks like here. This is Anders, who's actually responsible for this lab part. There you can attach this antenna, and of course, if you put it like this or you put it like this, you get 2 different things. And then what's happening at the turntable is that this can then rotate around like this. So if you rotate like this, you get 1 cut. Then you can turn it 90 degrees, and you can rotate it 1 more time like that, and you get another cut. And in that case, you can get 2 cuts. And the typical cases here is that you measure what's called the E plane and the H plane. So you take the dipole, this one we radiate with an electric field dominant like this. So if I have it like this, I have the electric field pointing like this way, and I rotate it like this, I will get the E plane. And then I do like this, I rotate it 1 more time, then I get the H plane that sits here. And then I have the 2 cuts of my antenna, and you will get out the raw data for this. You have to process the data, and then in your lab report, you of course have to plot your data like this. So you have to plot it in this kind of polar plot. And in the beginning of the course, we had some exercises where we actually plotted these things. So there you have to plot this yourself. So you have to use either Orphanides codes, the codes that I suggested in the exercises, or you have to write your own code to try to plot these things in some reasonable dB scale to get this out. These are in linear scales in this plot I have. And these measurements are then done in what's called an anechoic chamber. So exactly the same photo as before, but now you can see all of these things that sits here. You can see these things that sits here. And these are these absorbers. So the anechoic chamber, it stands for an anechoic, and it means non-echoing or echo-free chamber. So if you send the electromagnetic waves to these walls, it doesn't come back, it gets absorbed. In the same way in the acoustic one, when you speak, you know, your sound goes out, it hits the wall, it gets reflected to the wall, and it actually comes back to you. There's an echo coming there with a slight time delay. In these ones, what's happening is that it hits this material, and in this material, it gets absorbed. So it doesn't get radiated back. And that means that for the antenna, it looks like it is in free space. There is not an environment around it. And that's how you would like to measure your antenna, because you would like to know what is the gain of this antenna in free space. Then if you add something afterwards, you can do that afterwards. But you would like to measure it in these cases. So the anechoic chamber is really to, emulate free space. It looks like there are no walls. Then you could say, why don't we just measure it outdoors instead? Because outdoors there are no walls. That's true. There is a ground, so we could just cover the ground. But at the same time, you can start thinking now outdoor. Okay, now it's December in Sweden. It's pretty cold. So of course, you don't want to do all of this outdoors. There are many measurement ranges outdoors because you don't have to do this cover of the rooms. But then you can only measure when the weather is nice. And you would like to, of course, measure whenever you can in some ways. So the trend is that everything is basically built in today, unless it's so big so you cannot do it. I will show you some of those cases. The materials that sits here on the walls, those are called as radar absorbing materials, RAM, and they typically looks like this. So this is one. And in the lab here, they will let you touch one of them. You should never touch anything inside of this room. When you go into this room, don't feel tempted to touch anything because you will destroy it and you get very black of your fingers. So don't do it. They will give you one of those to play with outside if you want to touch it, because many people want to touch it when you go into a room. Or if it was a lecture, I could let you touch this one. This is a soft one. These are hard ones, which make your fingers black. The one I have here, don't make my fingers black. The one in there will make your fingers black. So don't touch them. You basically destroy them. And it is a material, so when the wave comes here, it doesn't bounce back. It gets absorbed into these ones, the electromagnetic wave. And the shape of these ones are in most cases pyramids. So they look like these pyramids sticking out. And that means that the wave can come in, it bounces a little bit, and it gets absorbed. So that's a typical anechoic chamber. And now when we do these measurements, of course, we need to know that we are far away from our, between our antennas, that the distance is large enough, so we can actually measure the far field. So that is a requirement that we've had so far in the description. I will show you later that there are different ways of doing this and also ways to actually measure in the near field. In the course here, we have really mainly focused on antennas in the far field. And I showed you expressions before which are in the near field. And one thing that you can see with those is that they are much more complicated. And in this course, far field is in some ways complicated enough. So that's why we have stayed in the far field description. Most of the things we have done can be done in the near field, but it gets much more complicated. And if you do some more detailed analysis of this, we can see that we can actually divide space as something called reactive near field, a radiative near field, and a far field. And this is, of course, where we've been sitting. So we, in some ways, need to know what is the far field. If I have this antenna, how far away do I have to be of this antenna to be in the far field? What is the distance there? So how far do we have to move away to become go into the far field? And if we look at the expressions of just the fields to understand what's happening here, if we take our dipole antenna and our very short dipole, so Hertzian dipole, this is what the electric field looks like. So you can see here, okay, it looks fairly complicated. If we now write this for a dipole that is directed in the Z direction, so we can use it with theta angle and phi angle around it, it simplifies a little bit. So the electric field now will have one radial component and one theta component. And what we have done in the course so far is really this one. This is the far field of this dipole. If you look at the terms here, you can see that this one goes as 1 over R2, 1 over R2, and this is constant plus 1 over R, while the one that we had in our far field over here only decays as 1 over R. So that means that when you take this antenna and you go very close to it, what dominates is actually these components. Those components are much stronger than these components, because if R is small, those components blow up and they get very strong. And that means you have come into the near field of the antenna, typically the reactive near field. So around this antenna, there's a very strong field that's just pumping forward and back. And for example, in cellular phones, that's what you have to deal with this SAR, because your cellular phone you put close to your head, and then you are actually inside of this reactive field, because you're within like a wavelength of this at these frequencies. When you move further away, then these terms disappears and this one dominates. And that is where we would like to be in our measurement. So of course we need to know how far do I have to go to reach this far field in these cases. And if we look what's happening, exactly as I mentioned, the first one, the decay, and the next one stays as 1 over R. So that is the one that we actually will have in this course. So doing these divisions into these regions, we have the first one, which is the reactive near field, and that is this close to the antenna where the field is just pumping forward and back like this. And then you have a radiative near field. Then you are somewhere here. So you are far away from your antenna, so the field is not really going like this. But in some ways, you could say you have an angular resolution of your antenna. You are so close to these ones, so you really clearly can distinguish different pieces of it in some ways. When you go to the far field, it just looks like everything is coming from the same point of it. And that is, of course, then what you're outside here. That is the far field. And in the far field, you have this decay of the field. So the field goes as 1 over distance. So if you double the distance, the amplitude also goes a factor of 2, the power goes a factor of 4. And the electric field can really be written as something like this. So it only have one term here, and this one, the terms depends then on the direction r hat, which is theta and phi. So only the angular part. The distance part is separated from this. So here sits the distance and there sits the distance. So we separate angle and distance. When you are in these near fields, there is no such separation. these angles in some way, so the shape depends on the distance and so on. And in most cases here, we make a definition of what is the far field. So it's like a rule of thumb. And the rule of thumb says that the distance r has to be greater than this number here, rf, which is 2 times the dimension of your antenna divided by lambda. And the dimension of the antenna is really the dimension of your antenna structure. So if you have a parabolic reflector, how large is this reflector? So you square that, you divide by the wavelengths, and you multiply by 2. If you have a small antenna, it also says that the distance should be greater than the wavelengths, or much greater than the wavelengths. In practice here, usually like at least 2 wavelengths is a rule of thumb. So that is in some ways where you have to move away from your antenna to be closer to this far field. And it's sometimes called the Fraunhofer region of this one. That's more a physics type name for the same thing. So that is our far field. So if we try to understand what this means and what it means from what we see with it. So if I take 2 Hertzian dipoles, so I have 2 dipoles here radiating, that sits there. They are separated a distance d. And now we say that the distance now is 2.5 lambda from each other. And then I can just move further away from this antenna, and I can look at what is the shape of this antenna. And when you can see that you're very close to it here, so the distance in x, you move away, is now equal to d, and then I move it up to 13d. You can see that things starts to change inside of it. It looks slightly different when you move away. The largest effect of these ones is that, of course, this goes over fixed angles out there. So you can see they have some angular pattern out. And that's why in most cases we plot this in polar coordinates instead. So we actually plot it as a function of the angle, not as a function of the height in these cases. And that is what's done down here. So here we see the same plot, but in polar plot. And now if we take a closer look at that one, you can see when r is equal to d, so I have the first one. What you can see here is that in some ways you don't get the very sharp nulls. So when the distance is larger, you can see here you go down to very low values. But when you are at r equal to d, you don't get these dips. And these dips is like a perfect destructive interference. You get a cancellation really that comes there. In the near field, that tends to disappear. So in some ways, I need to move further out. So if I go a little bit out here to 3D, you can see it starts to filling out or filling in. And when I go further and further and further out, yeah, they actually start to come into something that looks like these real dips that sits there in some ways. And that means that to measure this, I need to be far away because I would like to really get this shape out of it. And if I'm too close, you know, I get something here that's a little bit smoothed out version of it. And that is again this distance that comes in. And if I look at this and we compute the far field distance, in these cases it would actually claim that the far field distance is 5d in this case. And that means that actually this one would be that you are in the far field, and that is the green curve that comes down. So you can see it's not even perfect when you are in this part. It gets better and better the further out you go, but at least you get most of the shapes. You start really filling out the dips quite well, not precisely. So this is a rule of thumb where you have to be, to in some ways be in the far field. So now comes my question to you. You have all this week built a patch antenna. So you basically made your own patch. I think I had your patch here somewhere. No, I don't find it. Similar to this ones, but you build your own patch. You did it for Bluetooth frequency. So what is approximately a far field distance of your patch antenna? How far away do you have to be from your patch antenna to be in the far field? What do you think? So in these cases, I will open up a poll very soon here. Question A, 25 centimeters, so something like this. Half a meter, 1 meter, or 2 meters. Where do you have to be? How do you determine it from the patch antenna that you have all built? Oh, here I have it. Here I have your patch. Same as you have built, all of you. How should you determine the far field distance from this? What can it be? So again, in these cases, A, 25 centimeters, B, half a meter, C, 1 meter, D, 2 meters. What do you think it is? So you get 10 more seconds to a few more answers. We're up to 60% today. Okay, we stop there. So this is the response here. A and B, you have to be either 25 centimeters, 50 centimeters, and 2 meters also get one response. So of course, to do this, we have to calculate what we should do. So let's take a look at it. So let's close down this one. So first of all, how should you determine it? Yeah, you have to use the formula that we had. And of course, in this case, we had this RF, which was 2d2 over lambda. So if we start with this one, what is lambda? What is lambda for your patch antenna? You have all measured it this week. And you know what frequency you used. So what is the wavelengths that you had? Any suggestion from you? What was the frequency for your patch antenna? Yeah, I got the formula. So what is it? How do you calculate it? Yeah, 0.12 meters. So that is the distance you have. And of course, how you calculate it, you know what 1 gigahertz is. That is 30 centimeters. You divide 30 with 2.4. Of course, it's maybe not you can divide it exactly with 2.4, but at least you get an approximate answer. You know, if you divided it with 3, you will get 10 centimeters. If you divide it by 2, you get 15. 2.4 is somewhere between. So yeah, around 12 centimeters. That is the wavelength. What is the D? What is the size of this one? I mean, you have your patch here. So it looks something like this. In your case, I think this one is 7 centimeters. So you have this one, this is 7, and this is 7. Oh, no, I cannot write 7. These are 7 centimeters. And your patch length here, if you feed it somewhere, you have some length here. This is basically lambda over 2 in the material. So what is your D in this case? So what is the distance that you have here? Or length of this one, or size of this object? So to make it really conservative in these cases, what you actually have to do is to take the entire structure here. So D will in that case be this one. Oops. So D will be the total structure that you have. You have your patch here, and then you will have your D, which is the diameter of this one. That is D in this case. And if the ground plane is very large here, that will overestimate your D. And in that case, you can actually use that the most of the radiation comes from here, and you can instead use the diameter of your patch. It will also be a fair estimate in this case. And if you do all of this, you realize that actually your patch is so small. So this far field distance actually is in some ways limited with the number of wavelengths that you are away from something. So it's actually that you have to be at the distance, which is D2 over lambda times 2, but you also have to be a few wavelengths away. And that is actually what dominates in these cases. So if we do the calculation here, we can see that our wavelengths here, as I said, was 12 centimeters. But you also have the requirement here in some ways that D should be much larger than the wavelengths. That's a requirement. And the size of D, we can either use the ground plane, and that would say that D is square root of 2 times 7. And we can, of course, calculate it, and we will, in that case, get that it's 16 centimeters away. And if the ground plane is too big, you can instead use the patch, and that would, of course, give a even shorter distance, 5 centimeters. But in both of these cases, a more reasonable assumption of this is that at least you have to be approximately like 2 lambda away from it. So these are actually small antennas. They are not electrically small. They are like half wavelengths in size in this case. And what you have to do is that you have to be a sufficient number away in the size of it, but you also have to be a little bit away from the lambda. And the typical rule of thumb is 2 lambda. It's not a strict rule, but that's where we sit. And in this case, you would go actually to 25 centimeters. It's not strict, but it is in that order in some ways to be in the far field of these ones. So that means that we know what's happened to the patch approximately. If we plot in that the structure is D, we will get the same here, then we get 2 lambda. Let's do a few more interesting ones. If you do an array here with 10 elements, so something like, this I've shown you before as array antennas, and you space them with lambda over 2, that means that your size here, it's a 1D array, is approximately 5 lambda. And that means that your far field distance will be 50 lambda. If you do that with your antenna, and you say you're operating at 1 gigahertz in these cases, your far field distance here is 15 meters. Is that a lot, or is it not a lot, or what do you think? If you think that you're sitting, and if you are a base station, and you have your users away from you, 15 meters is a good distance. If you think that you, for example, do channel measurements as done with these type of antennas, and you're sitting in an indoor environment, rather few rooms are 15 meters in size. Which means that in an indoor environment of these sizes, you're actually usually not in the far field of these kind of structures with these many number of elements. It depends, of course, of the frequency and so on, but you can get actually pretty large distances rather rapidly when you start increasing the size. If you do another interesting one, let's do this one. Let's do this parabolic reflector I showed you also pictures about for arrays. The diameter of these ones are approximately 25 meters. And if you use a wavelength of 3 centimeters, so somewhere in the mid-range of this structure, your far field distance is 42 kilometers. Do you think that's a lot, or what would you say? Do you think it measures something that is in the near field of that device? Of course, in operation, this is looking at galaxies and stars far away. So 42 kilometers is absolutely nothing. So everything it's looking at is really in the far field. But of course, if you would like to characterize these ones, it's pretty challenging. It's hard to be in a measurement chamber that is 42 kilometers of size. You cannot really do it. It's impossible. If you take another case, take a red laser, laser pointer. They have a diameter typically of around 2 millimeters. And if you take a wavelength for those, it's like 0.6 micrometers. It means that they have a far field distance of 12 meters. So what I try to say with this is that you really have to look at the size of the structure, because of course 2 millimeters for a laser, it's physically so small. But if you have a laser point, this beam that goes out, beams don't exist in the far field. They are all near field parts in some ways in these settings. They are not reactive near fields, but they are not in the far field. And the far field distance of here is typically what you can have in a larger room in some ways. And that's, again, you get a nice beam that propagates, because when you go in the far field, you always have this diverging thing that goes out, like on a spherical structure. But the laser beam, it goes straight forward. And that's because it's not in the far field. There is a difference between these two. So electrical large antennas, which we have in these cases, like both of these ones, they actually require very large measurement ranges. And we need improvements to, of course, measure those ones in an indoor environment. So I will show some of them now. So one is what's called a compact range. And one version of this, you can just see a picture, I'll come back to it soon. One is sitting down there. So what you try to do in all of this measurement system is that you have to build some anechoic chambers, and that's because you need to measure in all type of weathers. That's really the requirement. You need to protect what you have there. And then the size of the far field really determines the size of the antenna under test. If something is big, you cannot measure it in the far field range in some ways. You have to remake it. And what you can do there is that you could put reflectors. And if you put a reflector in one of these, you can actually make the antenna chamber smaller. That is what's happening in compact ranges like there. Here you can see a typical base station antenna. I will show you the reflectors that sits there, because you don't actually measure those to the far field of that array antenna, but you put the compact range that actually produce a far field range. You can use near field ranges, which one is, for example, here, where you can measure around these devices, and then you use algorithms to transfer things back and forth and so on. And there is another one that's become quite popular recently, which is called reverberation chambers, which try to emulate a random channel, like you have waves from all directions. So you don't try to measure in free space. You actually try to measure more in a realistic space. So a compact range, what it can look like is that you put in some reflector. So this is a reflector that sits there. And what you do is that you have some, here you can have a feed. So this one illuminates the reflector, and then the reflector bounces the wave back. So here you have a curved wavefront, and here you will get a planar wavefront. And what I mean with that is that the curved wavefront is this spreading out that it does like from an antenna. But then with the reflector and shaping it, you can go like a plane wave, and that means it looks like the far field of this one. And then you put your antenna here in a specific zone, and it actually measures it as it was in the far field of this one. So you transform this feed with the reflector to look like it was further away than it was, in the same way as you do in optics with the lens in some ways. These are measurements for antennas that sits behind here, but it's actually most for what's protect antennas, which is called a radome. And this is for a fighter aircraft in this case that try to protect the radar antenna, and you do similar type of measurements. This is one in Mölndal outside Gothenburg. So this is Ericsson chamber. And here you can see a base station that sits here. Here you can see the transmitting antenna, and it sits a reflector here. So this one goes there through the reflector and it bounces there. Or it can, of course, go the opposite way too in these cases. So you have a reflector there that makes the room small, and you can see the size of this one. These are enormous rooms. You see the same thing that you will see next week with these cones, but of course these cones are bigger, and you can basically see that everything is covered by this. And that is to reduce all of these unnecessary reflections. You can do a near field range. So there are different types of them. So in this case, you actually measure in the near field of the structure, and then you use algorithms to compute things. So in these cases, you actually measure both amplitude and phase. In the far field range, it's usually sufficient to measure the amplitude. It's done on the different geometries, typically spherical, cylindrical, or planar geometries. And then you do calculations to give you complete 3D patterns. And this requires more advanced techniques. But when you have it, it's very good. For example, you need to compensate for your measurement probes because you're in the near field, so you actually don't know the direction the waves are coming to your antenna and so on. And then you can, in some ways, compute what the far field is from these near fields in these cases. These are some photos here. So, for example, this is from Microwave Vision or Satimo, nowadays Microwave Vision. Here you can see a cellophone around the head. So you can actually, turn this one around, and then you measure at the same time. Here are the antennas that measure these ones. This is a base station. It's a person with a laptop, so you can understand how the waves are coming out from it. And here you can see a car. So of course, the car has a larger range than the person that sits first, but the principles are the same. These are antennas that sits here. And you try to have many antennas to speed up the measurements, because otherwise these measurements are very time consuming. This is a cylindrical set. A cylindrical set is sometimes simpler to understand because you rotate these ones and you move the probe up and down here. So by moving the probe like this and rotate, you get a cut on the cylinder, and then you can use this to analyze the data that's radiated, or you can actually try to analyze what was the thing that radiated, which are some pictures that are seen here. But I will not go into them since we are actually out of time. I will show you a planar case instead. Okay, so this should be a movie that starts, but it doesn't. So in this case, you can think you can move these ones here along different lines, and of course you can move it like this. And then you can scan the area here over a planar region. And if you do it over a planar region in these cases, you can actually use that to transform to the far fields. It's also quite efficient technique. And one of the last techniques that has to be done in all of these measurements is called SAR measurements, which are slightly different. It's not for the antenna parameters. It is for this specific absorption rate. And these are standardized. So if you make, for example, a cellular phone or something, they are regulated how much power they can in some ways radiate and how much could be absorbed in the head. And that's due to heating effects and so on. These are some simulation pictures here where you can simulate your device close to the head. You can see here, these are pretty old because the antenna is actually sticking out. And in some ways, if you get a lot of radiation, which you can have at lower frequencies particular, of course, you can get heating. And in this case, there is SAR that measures in some ways what is the maximum absorbed heat compared to the density of your device. And that is in some watts per kilogram, and it's standardized how much that can be to be below the levels what's allowed in some ways. And the measurements of these ones are typically done by moving a probe into a model of the human body. So you can see a probe here, and it's on the table, and this robot moves this probe, and it does it down here in something that is a model of the human body in some ways, which is filled with a liquid that looks like our electromagnetic properties, like losses and dielectric and so on. And then you move this probe and you figure out where is the hotspots and so on, and make sure you're below the levels that you're allowed to be. And that has to be done for all of these consumer products that are sold. So that's the SAR cases. Nowadays, we go up to millimeter waves. We'll take 1 more minute approximately. So you know it's coming now, this 5G and millimeter waves, like 28 gigahertz and up. And in those cases, you actually measure in a little bit different ways because the frequency is very high. The physics is slightly different. You have a very rapid attenuation in a lossy body. So it's almost like a skin effect that happens there. And the EMF compliance in these cases are mainly done what's called the incident power density of these ones. So you measure what is the power that actually can come out from your device, very close to your device, and you say that has to be below a certain value over some average site in some ways. And it is partly standardized now, but it still works on all of these things that what will happen with cellular communication, for example, at higher frequencies. So that was basically it about measurements and measurement techniques. So what we are doing now is, of course, that this week is over, and next week we will start moving to aperture, horn, lens, and reflector antennas. And in these cases, reflector antennas is now your new, very interesting antenna. Because now you have built your own patch antenna. You have built 2 patch antennas. We will measure them next week. But on the lab that you come to next week, where you will measure your patch antenna, you will actually also bring your reflector antenna. And on Monday, we will talk about reflector antennas. So there we will learn how to make a reflector antenna, and then actually you yourself have to build your own reflector antenna. And the typical ways of doing it is with the kitchen tools that you have at home, typically aluminum foil. So you need to have some ideas, how do you do a reflector antenna, and then you build it, and we will actually measure that in that lab. And again, as I said, you can already sign up for the lab. The lab is next week. And to that one, there will be a quiz. It's opening up probably tomorrow. You have to bring your antennas, bring your reflector antenna that you build yourself, and of course do the quiz. Now the 4th quiz is closing. The 5th quiz has already opened, so you have 1 week to do that one. And yes, next week, lab sessions with these cases. So